Hello everyone, welcome to lesson 16 and 17 notes for BCA tables, limiting reactants, and percent yield. We're going to go over the do now using a BCA table. So if you have 15 grams of calcium chloride, how much silver chloride in grams can you produce? It's helpful if you do a roadmap. Please make sure we're paying attention. And in case you missed it, I am coming live from third period this time. Sweet Jesus, sit still.
Sorry.
Okay. When we're given grams, what should we always convert it to? Moles. And then we can convert it to moles of something else, right? And so in this case, this is moles of silver chloride. This is using the bigger mole map that we have. So we have grams given and we change it into moles given. Then we can change it into the moles we want, but we actually wanted grams, but we know we can go from moles to grams using the molar mass. So we're going to do this. So step 1 is a molar mass conversion. Step 2 is a BCA table. And step 3 will also be a molar mass conversion. Okay, so we're going to do our first step. So 15 grams of calcium chloride. And we're going to change that into moles. And I'm kind of out of room. Oh, well. Well, not oh, well. I need actual, room. So, mole on top, what goes on bottom? Grams. Okay, how many moles? 1 mole has what mass? 98. Okay. So, 15 divided by 110.98 is what? Is that correct? Am I remembering it right? Oh. No, then I did not remember it right. It is point what? 1 more sig fig, please. There we go. As a reminder, 3 sig figs at least, because you are given 3 sig figs. Okay, so now we know our moles. We can now use a BCA table to change our chemical formula. We're using a BCA table here because it's going to lead us into review for the notes that we will cover. So zeros for our products, zeros for our reactants, because we're only given 1 reactant, and then fill in our given. Okay, is the reaction balanced? Oops. I see 2 nitrates and 1 nitrate. It is not balanced. How do I fix that? What's the coefficient for calcium? 1. What's the coefficient for silver nitrate? What's the coefficient for silver chloride? And calcium nitrate is 1. Okay, now we bring our coefficients down for the change. What goes in the what column can we use to find out our parentheses? The first one, because the parentheses is the only thing that's blank. So what goes in the parentheses? Yep, and that goes in all of the parentheses. And then we use a calculator or our brain to figure out the rest. What did our problem ask us for? AgCl. So I have moles of AgCl here, or silver chloride. Okay, and I said I wanted grams, so I need to change it. How many moles? Huh? No, that's the balance equation. So 1 mole has what mass? So the coefficients are only used in a BCA table or when we're changing our chemical substance. We don't use it in the molar mass because the molar mass is defined as the mass of just 1 mole, which is also why we don't multiply this by 2 or the coefficient from the reaction, because it is always just 1 mole. If we multiply it by the coefficient, we're saying it is multiple moles. So solving this, we end up with, I think we said 38.7 or something. Remember that this can vary slightly because of rounding, okay? And it is your uncertain digit. It is meant to vary, okay? If you get it right on the mark, yay, that won't happen every time. Okay, any questions on this one? Okay, so page 15 starts our notes on limiting excess theoretical and actual yields, and it'll discuss briefly percent yield. So the limiting reactant is the one that is used up in a reaction, and this controls how much product you can make. The excess reactant is the one that is not used up. Sometimes you are told that it is in excess. Sometimes you have to figure out if it's in excess, and this one you have leftovers at the end. Theoretical yield is how much you expect to produce. This is always a calculated value. You cannot measure it. It comes from doing our BCA tables, our dimensional analysis, and figuring out how much we could make. The actual yield is a measured value, and that comes from an experiment, or I give it to you sometimes. Okay, if it's like a practice problem, I will have given this to you. Whichever reactant makes less product is the limiting reactant, and this dictates how much product can be formed before it runs out. And there are several steps that we will walk through on page 19 on how we can figure that out. Notice that it is a BCA table because we have multiple reactants given to us. Okay? So that is something that's going to happen here is BCA table. Can you do it without BCA tables? Yes. Is it a greater pain in the butt? Of course. So we use a BCA table. We're also going to discuss on pages 19 and 20, I think the actual practice problem is page 20, percent yield and how to calculate that. And we'll go into more detail when we get to that one. So please take a second and flip to page 19. While you do that, I'm going to read. So on the mole maps, they aren't above because I forgot to copy and paste them in. My bad. We can only go between boxes or bubbles that are directly connected by an arrow. So if we're given grams of something, so given grams, but we want grams of something else, we know we have to go grams of A or given to moles given or A to moles that we want of B to grams that we want of B. We can't go straight grams to grams. We have to change it to moles first, okay? Moles are like the great crossroads of stoichiometry because it goes to everything. So another example, we're going to use a BCA table for this one, so we're practicing. So how many grams of iron 3 oxide are formed from the reaction of 5 grams of iron metal with excess oxygen gas? When we first do these, the one thing we should always check is the reaction balanced? Is this one balanced? No. I want you to now take time, and if you're watching, pause the video to balance it now. Okay, so balancing this, you should have seen 2 and 3. Well, some of you may have written a 2 here because of iron, but then we see 2 and 3, those don't go into each other easily, so we would use a least common multiple, and that would be 6. So 2 times 3 gives us 6 oxygen, and then 3 times 2 gives us 6 oxygen, but that makes iron 4, so I fixed this one on this side to 4. So you should have gotten 4, 3, 2. So your first step before you do anything that's stoichiometry is to make sure that reaction is balanced. I won't trick you and give you ones that are unbalanced but have coefficients. So if you see coefficients, it is generally safe to assume that it is balanced. Okay, So this is a straight up like stoichiometry. I'm not giving you limiting or excess. We're reviewing. So we are given 5 grams of iron, which has the element symbol Fe, and we want to find grams of iron 3 oxide. So I want you to first convert, right? Our first step is to change grams of iron to moles of iron, so then we can use it in the BCA table, right? Because our second step is to do the BCA table. So I want you to do step 1 now on your own. Please pause the video if you are watching. Okay, so here you should have gotten 0.0895 moles of iron. Okay. So now we can set up the BCA table. I want you to now, after checking your work, pause the video if you're watching and set up your BCA table, including filling in the parentheses. So do your whole BCA table and we'll check as we go, check at the end. Okay, so you should have, what's the what? No, that's how much you start with, right? So this is the total amount that you start with, right? The X is how many times you're going to run that reaction if you think about it. The coefficients is the ratio that they're going to react in and whether or not you're using them up or making them. So we wanted to know moles, well, grams of the iron 3 oxide. We know the moles of the iron 3 oxide, so we now can convert that. Right? So you're going to convert it into what? What do you change it into? Grams, right? And the moles come diagonal because we do the disco. So please solve that for yourself. Pause the video if you're watching. So you should have gotten, and we're rounding to 3 sig figs, 7.15 grams of iron 3 oxide, right? Remember that this can vary slightly. So if you round it a little different, or you actually round it as you went, I was using unrounded numbers, thanks to fancy graphing calculators. Rounding at the end is best, using more sig figs as you go. Cool? Any questions? Because I'm going through it again. It's like the more repetition you have, the more your brain connects all that stuff.
You go back.
Uh-huh. Okay, so here we go. Limiting reactant, when the amounts of both reactants are given. Now, there was a spoiler in lesson 15 on 1C and 2C where I told you BCA tables will make this easier. Those were limiting reactant problems. My bad. Sorry, but you guys did it. Hey, you're smart. When both reactants are given, like we have 2 given values, we have to determine which one is limiting. That means that one of those limits how much product can be formed. The other is in excess. And you know this when you do the math, you have to pick your numbers when you're solving it so that you have no negative amounts for your befores or your afters. Okay? So here we have 10 grams of iron reacting with 15 grams of chlorine gas. How many grams of iron 3 chloride will form? Okay, so we are given 2 values and we want to find one. So this is where a BCA table is the best fit. Okay? For any stoichiometry problem, what should you do first? Balance it. Balance the reaction. Okay. So then I heard map it out, and that is a very great place to start. So we here have grams of iron given and grams of chlorine gas. And we want to change those into what if we're going to use a BCA table? Moles. And then we can find from both of these the moles of what we wanted, which is iron 3 chloride. And then since it asks for grams, we can go to grams of the iron 3 chloride, right? Here where they converge, we use a BCA table to reduce the amount of work we use and allow us to see all the numbers all together. Okay, so we have 1, 2, 3 steps. Okay, so for our first step, you guys are going to, if you're watching, pause the video, or in class, you're going to solve for the moles of each one. Please do that now. So you should have gotten 0.179 moles of iron and 0.212 moles of chlorine gas. Okay, we are going to do step 2 together because the BCA table, when we do limiting reactants, there's a little bit of a trick that we have to pay attention to. You may have figured it out already, but we're going to do it together. So we're going to set up our BCA table mostly like normal. So for our products, we know we have no products at the beginning. But our reactants, we're going to fill in what we have at the beginning for both in the same table. So there aren't 2 BCA tables. The goal is to reduce your work, not make more of it. Okay, but because we have 2 given values, we do not know which one of those hits 0 first. So we cannot put in 0 for the reactants after the reaction yet. We will for only one of them in a minute. So we're going to skip the zeros for after for the reactants, and we're going to pull down our coefficients for the change. So pull down your coefficients for change. Okay. And typically our next step would be to figure out what goes in the parentheses by looking at our givens as if they go to 0, right? So if you haven't figured it out yet, you're dividing by the coefficients. So I'm going to divide this by 2 and get a number, and this by 3 and get a number.
0.1534 for gas, and then 0.179 for iron.
Dividing by 2? Divided by 2. Huh?
Oh, sorry. Those are my final thing. Yeah, 0.0895 and 0.767.
0.07. Okay, are my values correct, guys? Okay, so when we do these, we divide both by the coefficients because we're going to see which parentheses value. So these are our possible X choices, right? We've said like, hey, in the parentheses, we say this is X. And we're now saying we're going to pretend that these might get to 0. We're going to see which one gets to 0 first. So the X for iron might be 0.0895. The X for chlorine gas might be 0.0760. But remember, our parentheses, all of them, because they're all X, they all have to be the same number. I can't put the one from iron only in iron and the one from chlorine gas only in for chlorine gas, right? Because I don't know then which one I'm going to use for the iron chloride. They are all the same number. Because this is a limiting reactant one, I am limited by my smallest. So guess which one we pick? The smallest. Okay? So out of those 2, I'm picking the smallest to go into all of the parentheses. So 0.076767 goes in all of them. I can't talk this morning either, so it's great. Okay, so now that we have those, we know that since this is limiting, if we did this math, 0.212 minus 3 times 0.0767, we know that that one should hit 0. Okay, if we do sorry, I'm trying to catch up. Oh, that is already there. If we do the iron column, we get 0.0380 left over, or in excess. If we had picked iron's X instead, we would have seen a negative amount in this column. You can't use more than what you're given. So if you end up with negative after values, you owe the universe matter. You created matter out of nothing or made it disappear. No, you created matter out of nothing. That doesn't happen. It has to come from somewhere. So you fubbed up your math. They can either be positive amounts of matter or it can go to zero because you used it all up. So we would say that this is an excess and that our Cl2 gas is limiting. And then 2 times our parentheses is 0.141. Yeah? Oops, no, I put in the wrong thing. Hold on. 2.212 divided by 3. This should actually be 0.70. Somebody's giving me the wrong stuff. I think we divided by 70 and not 70.9. Because 15 divided by 70.9 is 0.212. Then we divide by 3 to get our x. Is 0.0707, not the 6. Okay. And that is our parentheses, and so this should be 0.141. There we go. We fixed the math. That is still correct because I had it stored in my calculator as 0.0707. Or 0.705 if you're rounding. We can do this. Here we go. All the way correct, unrounded. Miss Bert's fixing everything because some of the math got funky. And we are live from third period. Welcome to the Math Brain Exhausted on Friday. Okay, so we were asked for which, are we good now? What were we asked for? Which compound? Iron 3 chloride, so this one. Is it in the correct units though? No, we have moles, so we're here. Where do we need to go? Grams. So grams on top because we want to change it there and disco the moles. 1 mole has what mass for iron 3 chloride? That sounds very familiar. So we multiply across the top and we get 22.9 grams of iron 3 chloride. Okay, don't lose track of that number. We're okay with this? Questions, concerns, comments? Okay. Yield. Percent yield is the yield of the reaction that tells you how well the reaction worked in terms of forming a desired product. Generally, less than 100% results are obtained. If it's over 100%, you either have like a contaminant, the reaction didn't go all the way, it's still wet because you didn't evaporate off all the water or solvent. If it's less than, maybe the reaction didn't have sufficient time to run, a side reaction happened, you lost some of the product, and so on. Okay? So here's the general equation where we have actual over theoretical times 100, or your experimental divided by the calculated times 100. So it's kind of like what you should have gotten on the bottom. So if you're talking about your quiz score, what you should have gotten on the bottom, 30. What you actually got on top, 19. Times 100, okay? So, like, your grade can fluctuate. It can vary, right? So can your yields. So let's look at this. A student performed the experiment that we solved previously. So that yield was 22.9 grams that we calculated. So this was a calculated, if I can spell calculated yield. When they measured out the amount of iron chloride that they had generated, they found that they had 18.9 grams of iron 3 chloride. Calculate the percent yield. So remember, the percent yield is our actual or experimental over our theoretical, and I actually like the word actual, over theoretical. Yeah, actually. Times 100, okay? So your actual yield was what? What did you actually make, or what did the student? 18.9 grams. And what should they have made in theory? 22.9 times 100, and you should get 80 something. I know, right? Addison, did you get it or no? Thank you. 82.5, and look, correct sig figs used. Cool? Okay. So that concludes the notes. Answer the guiding do the work, answer the guiding questions on page 15. And there we go.